Hello and welcome to the live session of Advanced Reaction Engineering. So in this week's lecture, we're going to study about solid catalyzed reaction and diffusion. So in a heterogeneous catalytic system, the reactant in liquid or gas phase and the catalyst is in the solid phase. So the catalyst possesses a number of pores. The internal surface or catalytic sites are not accessible at the same concentration as it by the outer surface by the reactant. So the reactant concentration in the internal surface of the catalyst pellet is less than the external surface. So what happens is the rate of reaction is varied from point to point in the catalyst pellet. So if you see this example, the reactant A diffuses from the bulk fluid to the external surface of the pellet. Then it diffuses from the external surface to the internal surface through the pores. The reaction takes place on the catalytic surface. So what will be happening? The pores within the pellet do not follow a straight and cylindrical structure. Instead, they form a complex network of twisted and interconnected paths consisting of four bodies and four throats, varying cross-sectional radius. So if we consider an average diffusion occurring at any given position within the pellet, the radial flux will be calculated based on the total area perpendicular to the direction of diffusion transport, which is 4 pi r square. So the bulk diffusivity and the Knudsen diffusivity, they relates by this formula. d equals to dA psi p sigma c by tau bar. The path of diffusion is tortuous and pores are of varying cross section. So the constriction factor sigma c accounts for the variation in the cross section area, which is normal to diffusion. And sigma c is a function of the ratio of maximum to minimum pore areas. So when two areas A1 and A2 are equal, then beta, which is the ratio of these areas A1 and A2, this will be equal to 1, and the constriction factor is everything. When beta equals to 10, the constriction factor is approximately 0.5. So here you can see the derivation of the differential equation describing the diffusion and reaction in a single catalyst pellet. So you can see this 12 molar counter diffusion at constant total molar concentration. So the flux it will be coming as this W air equals to minus d dCA dr. So ultimately, the differential equation for different differential reaction, diffusion and reaction in the pellet, it will be this equation ddr of r square to minus d dCA dr plus r square k double dash SA rho c Ca to the power n equals to 0. So if we differentiate the first term and divide through by minus r square dV, the final equation will become as 2 by r dc dr minus kn by d Can equals to 0. So the boundary conditions are like this. Ca equals to finite at r equals to 0 and Ca will be equals to Cas at r equals to a capital R. Yep. And like this derivation continues. You get this telemodulus equation. Telemodulus is phi n square equals to kn r square Cas to the power n minus 1 by dE equals to kn r Cas to the power n by dE to Cas minus 0 by r. So equals to surface reaction rate by rate of diffusion. So if telemodulus is large, internal diffusion usually limits the overall rate of reaction. If telemodulus is small, surface reaction is usually regulated. So for a first order rate law, minus RA equals to K1 CA is d2 psi d lambda square 2 by lambda d psi d lambda minus phi 1 square psi equals to 0. Ultimately, we solving the differential equation for a first order reaction. It's coming as d2y d lambda square minus phi 1 square y equals to 0. Psi equals to C by Cas equals to 1 by lambda sine hyperbolic phi lambda by sine hyperbolic phi. Okay. So if there is telemodulus is a small value, indicate the surface reaction is controlling. If the telemodulus has large value, then the surface reaction is rapid. Reacting consumption is very close to the external pellet surface and very quickly penetrates into the interior of it. So the internal effectiveness factor will be equals to the actual rate of reaction divided by the rate of reaction that would result if the entire interior surface were close to the external pellet surface condition. So eta will be minus RA by minus RAS. So it is easiest to work in the reaction rates of mole per unit time in comparison to mole per unit time per unit volume. So minus RA into volume of catalyst particle by minus RAS into volume of catalyst particle will be NA by MAS. So NA is equals to rate at external surface by volume into volume of catalyst equals to minus RAS into 4 by 3 pi R cube equals to K CAS 4 by 3 capital R cube. The actual rate of reaction is the rate at which the reactant diffuses into the pellet at outer surface. The actual rate of reaction is Mx equals to 4 pi R dE CAS d psi d lambda at lambda equals to 1. The psi equals to Ca by Cas will be equal to 1 by lambda sin hyperbolic phi 1 lambda by sin hyperbolic phi 1. So it will be coming after differentiation phi 1 cot hyperbolic phi 1 minus 1. If you see this particular ratio, Ma by MAS equals to 3 by phi 1 square to phi 1 cot hyperbolic phi 1 minus 1. Which is the internal effectiveness factor for a first order reaction. The spherical catalyst. So this graph shows us for different reaction orders the internal effectiveness factor. For zero order, the 5s naught equals to r square root of k naught by d c naught. For the first order, it will be coming as r square root of k1 by d, and the second order is 5s naught equals to r square root of k2 c naught by d. So for a sphere, phi 1 equals to r by 3 square root of k1 double dash SA of c by d. So equals to r by 3 square root of k1 by d. For a cylinder, it will be r by 2. And for slab, it will be the length of the slab. Yeah. So if the particle diameter becomes very small, phi m decreases so that the effectiveness factor approaches 1. And the reaction is surface reaction limited. On the other hand, when the Thiele modulus is large, say that phi m goes to 30, the internal effectiveness is small. And the reaction is diffusion limited within the pellet. And then the effectiveness factor for large value of Thiele modulus, it will be it equals to 3 by phi 1. Okay. If phi 1 is greater than 2, then it will be 3 by phi 1 square to phi minus 1, and it's very large, like greater than 20, then it will be the effectiveness factor will be 3 by Thiele modulus. Then we'll see the overall rate of reaction in terms of the Thiele modulus will be eta equals to minus RA by RA minus RAS. So minus RA will be eta into minus RAS, means eta into K1CS. So putting the values, so it will be 3 by R square root of K1 SaOC DE into CAS. For this, and this is valid for the first order reaction. Okay. So to increase the rate of reaction, what is happening? We have to decrease the radius R, which means that pellet we have to make smaller. We have to increase the temperature, increase the concentration of P, increase the internal surface area. These are the possible options because these are all the factors of the rate. As for nth order reaction, Taylor modulus coming as phi n square equal to Kn R square Cas to the power n minus 1 by dV. For large values of Taylor modulus, eta will be coming as square root of 2 by n plus 1 into 3 by r square root of dV by Kn Cas to the power 1 minus n by 2. So for the non-isothermal case, effectiveness factor can be significantly greater than 1. So when the reaction is exothermic, it's non-isothermal, the external surface temperature of catalyst pellet is less than the inside temperature when the exothermal reaction is taking place. Therefore, the rate of reaction inside the pellet is greater than the rated surface. So the effectiveness factor is the ratio of actual reaction rate to the rated surface conditions. So eta is the ratio of actual reaction rate by reaction rate at CAS. So if you see the RNS number, comma, is E by RTS, and beta is the maximum temperature difference that could exist in the pellet relative to the surface temperature. So beta is delta T max by Ts plus T max minus Ts by Ts. So if the thermal conductivity is low and the heat of reaction is high, the temperature difference is high. When multiple states exist, the values of the filling modulus less than 1. And when beta is greater than approximately 0.2, no multiple steady state can exist. The criteria developed by Luss is fulfilled, which is the 4 into 1 by 1 plus beta should be greater than beta into gamma. So based on that, we do the falsified kinetics. So there are circumstances under which the measured reaction order and activation energy are not true value. Consider the reaction rate data in a differential reactor, where I have to eliminate the mass transfer resistance. So if I have to do that, construct a log-log plot of the measured rate of reaction minus RA as a function of the gas phase concentration. So minus RA equals to Kn into CAS to the power N. The slope of the plot is the apparent reaction order N, and the rate law is measured as rate of reaction. Minus RA equals to Kn CAS to the power N. The actual rate as per consideration of the effectiveness factor is minus equals to eta star minus RAS. So minus RAS equals to Kn CAS to the power N. Ultimately, the apparent reaction order N will be related to the true reaction order. So the overall exponent of the concentration CAS that must be the same, okay, for both the analytical and measured rates of reaction. The apparent reaction order N is related to the true reaction order N by N equals to 1 plus N by 2. In addition to an apparent reaction order, there is also an apparent activation energy, E apparent. The true specific reaction rate in terms of activation energy equals to Kn equals to AT e to the power minus ET by RT. And the apparent specific reaction rate is in terms of activation energy will be Kn dash equals to A apparent e to the power minus E apparent by RT. So replacing the value of Kn in the rate of reaction expression will be minus R dash equals to 3 by R square root of 2 by dE 2 dE by n plus 1 into CAS to the power n plus 1 by 2 kn to the power half, it will be equals to kn dash into cs n to the power n dash. Ultimately taking the natural log both sides, giving us ln a apparent cs to the power n dash into minus e apparent by rt. So true activation energy is equals to the twice the apparent activation energy, et equals to 2 e app. The measurement of apparent reaction order and activation energy results primarily when internal diffusion limitations are present and referred to as disguised or falsified kinetics. And ultimately, there is a criteria for internal diffusion. It's called Weis-Prater criteria for quick estimation of which is the rate limiting step in heterogeneous reaction. Now, in this case, eta into phi 1 square is the Weis-Prater parameter. So eta into phi 1 square is equals to observed reaction rate by diffusion rate. Okay. So CWP equals to minus RA observed rho C R square by dCAS. So if this CWP is very less than 1, this particular value, minus RA dash rho C R square by dCAS, then there are no diffusion limitations and consequently no concentration gradient exists within the pellet. If CWP is very greater than 1, then the internal diffusion limits the reaction signal. If there is an external diffusion limitation, or there is another criteria called Mears criteria. So the Mears criteria is the measured rate of reaction if mass transfer from the bulk gas phase to the catalyst surface can be neglected. Mears proposed that minus Rn dash rho b into Rn by Kc to CAV should be greater than less than 0.15. If it happens, there is no concentration gradient exists between the bulk gas and external surface. Yeah. And finally, some examples which have been shown here. If there is any doubts, please let me know. Yeah. So that's all from my side today.